So here, exactly as with ANOVA, we'll partition the sums of squares so that we can get some kind of idea of hypothesis testing. So the residual sum of squares that we had defined previously was Ri squared, which we had written in this sense as B1 SSX minus 2 B1 SXY plus SSY. So if I rewrite this now, essentially all I've done here is I have taken the second term and multiplied and divided by SSX. And so what happens over here is SSXY over SSX is B1. So I've got B1 squared SSXY minus 2B1 squared SSX. So one of these terms cancels off, right? B1 squared SSX minus 2B1 squared SSX. So I get this term SSY over minus B1 squared SSX. So the regression sum of squares here is defined as B1 squared SSX, and the total sum of squares is SSY. So we can see the total sum of squares is the regression sum of squares, that's residual. So this is the total, that's residual plus the regression. So what I do here is exactly as before. We can partition the sum of squares. So the regression sum of squares, if you look at what we had as the expression B squared times SSX here, it actually works out to be the same as the difference between the fitted value and the actual mean of the data. And the proportion of variation explained by the regression, how much of the variation in the data, natural variation, that the regression explains is a ratio of the regression sum of squares over total sum of squares. And that's R squared here. This is simply what we also call correlation coefficient squared. We'll see this afterwards. Now, because essentially the regression sum of squares is not less than 0, the smallest it can be 0, then to kind of exceed the total sum of squares, that means R squared must lie between 0 and 1 inclusive. So now we can move on towards hypothesis test for beta 1. So the usual test here will be that simply beta 1 is 0 is the null hypothesis. That means there's no linear relationship between the x's and the y's. And we can have either a two-sided test or a one-sided test. And as before, in regression at least here, we would prefer a one-sided test if possible. So usually we have some idea of the direction of the change we're expecting or we're intending to engineer, which means that we will prefer to test the one-sided, one of the alternatives. If H0 is true, then the regression sum of squares will be very small, because regression sum of squares is B1 squared times SSX. This will be quite small because B1 will be small. And the total sum of squares is essentially the same as the residual sum of squares. In other words, the variation I'm seeing in the data is just random noise. There is no relationship there at all. So, as before, the problem here, as we saw with ANOVA, is that the sum of squares are based on different degrees of freedom. So, we need to adjust for that, and so we can essentially look at what's going on here. The number of degrees of freedom for regression with the number of parameters we are fitting minus 1. If you're fitting k parameters, that will be k minus 1. And for simple linear regression, k is equal to 2. I'm fitting 2 parameters, beta naught and beta 1 from the data. So that's 2 minus 1. And the total degrees of freedom as before is n minus 1. And the residual is n minus k. In this case, for the simple linear regression, it's n minus 2. And so I can set the calculations as before as an ANOVA table. And so we have simply here the sources of regression or residual and the total. And now with the sum of the square, the degrees of freedom is k minus 1, n minus k, and n minus 1. The sums of squares. And the mean sum of squares, I've also left out here the mean sum of squares of total, which we'll be using afterwards somewhere else. And the usual thing happens. The mean sum of squares are the ratio of the sum of squares upon the degrees of freedom. I get an F ratio here, which is the mean sum of squares of regression over mean sum of squares of residual. And that's an F distribution. The numerator has k minus 1 degrees of freedom. Denominator has n minus k degrees of freedom. And so I can get a p-value based on this F statistic, and I can test hypothesis that way. Just reminding you here that previously in the ANOVA situation, we used this as our estimate of variance. And here we have a variance as well sigma squared, and this will work out to be exactly the same situation. This mean sum of squares residuals is our estimate of variance in this case. We'll see that afterwards. Now, hypothesis test for beta 1, as we said procedures before, the F distribution looks a bit like the chi-square distribution. So all we do is we work out the probability of the p-value that F is bigger than the observed value. If that's less than alpha, then we will reject H0, otherwise we won't. In the Pharmax case, well, this is our total sum of squares we looked at before, as SSY and regression is B1 squared SS6. So these are the calculations. You will see what we've got over here is the table setup. You can work out the values for yourself. The value for F is 9.74, which is an F1 48 distribution. This is going to be our estimate of sigma squared for the FARMAX data. We'll see afterwards. And so my hypothesis here, if I do a two-tailed hypothesis test, the probability of F being bigger than my observed value is at 9.74. From R, this comes to quite tiny, 7.94 times 10 to the negative 8. That's much less than 0.05, our standard for the 5% level for two-tailed tests, two-sided tests. So this is a very strong evidence against H naught. So here we say that there certainly is a strong relationship between the sales and the promotions, and it's a linear relationship over here. If I do a one-sided test, all I do is I simply take the p-value and halve it. So if I want beta 1 to be bigger than 0, in other words, if I spend more on promotions, I actually sell more as well. So I simply halve the p-value, and that also means I halve the significance level. In either case here, I'll conclude there's a strong, significant, positive linear relationship between sales and promotion. Now we get to estimate the variance here, and we'll see that in the next lecture.